good afternoon. First of all, I would like to thank the organizers to be able to speak here and tell what we are doing in our company in the field of light checking optics, especially for illumination communication systems. So first of all, let me tell you a little bit about who we are. A company like Nanostructures, technically speaking, was launched in 2020, but as a part of the Optical holding exists since 2012, and the core team is together for more than 25 years. We started in the late 90s in the field of the security holography. We are based in the Czech Republic, in Škereň, a small village. You can see our site here. We have a small subsidiary in Brno focused on the development of TV writers. Our main focus of the whole holding is development, production, and sale of functional plastic products, micro and nanostructured surfaces, plastics, and parentheses, because recently we are also focusing on metals and other materials. In general, we are strongly focused on research and development. We have brought cooperations with academic sciences universities, not only in Czech Republic, but around the globe. And we strongly rely on in-house development to develop know-how and technology, so most of our technologies was developed and built in-house. The company is already quite big, so we have more than 100 employees since last year. Our main competencies, as I mentioned, design, mastering, and mass production of nanostructured elements. Optical is again in parentheses because we are now starting to focus also on functional surfaces for modification of surface properties and similar application of biotech as well. The holding consists of three main labs, three main companies. The first one is the biggest one. It's called Nanostructures, and it's focused on optical document security, which means it stays mostly on IDs and banknotes. So we have design, mastering, production, everything in-house. The second part, a company called Optical, is focused on general optical elements, not only for light shaping, also for imaging, but from business perspective, it's mostly about indoor lighting system, indoor LED lighting systems. And the third part, company like Nano, it was originally a service company producing the masters for us, but now they have their own program, and this is focused on development of 2PP-based 3D nanometers. So we brought to the market last year the first generation of our 2PP nanometer. For general public, these companies can seem quite heterogeneous, but you should understand that there's a common denominator behind. It's radiated micro or nanostructures. They have a little different parameters in these fields. In security holography, it's mostly about binary or harmonic gratings, sweet periods in hundreds of nanometers and depths of 1 or 200 nanometers for base gratings. In optics, it's more about, let's say, deeper structures, friendly surfaces, and it's more important to maintain the proper relief profile shape. With 3D nanoprinting, you know what we are capable of doing. Also, the general 3D periods in 3D are possible. The good thing, or the synergy from our daughter companies, allows us to combine the structures not only on top of each other, but also on the same substrate, which can be a big benefit, or is a big benefit in many application fields. So our philosophy is to do intense research, not only in terms of physics and development of structures, but also in finding new applications in new application fields. We are trying to have complete technology under one roof because we understood that this is a big obstacle. Cooperation is nice thing, but in this field, if you bring together 10 cooperants, then the process in the development can be quite long. So we are trying to have everything important inside in-house. And as I already mentioned, we are strongly relying on in-house developed technologies. Primarily, we are focusing on applications when there's a mass production behind, because we are coming from the holographic industry, so we know very well how to mass replicate the structures in terms of millions or billions of pieces. So we would like to use this expertise also in new application fields. So why nanostructured optics for lighting systems? So first of all, from a business perspective, it makes sense because new functionality can save energy, for example, so it's effective and visibility behind, because there's a lot of LED lighting system these days, but there are also good physical reasons behind it. In the old times, when we were using bulky sources like bulbs and fluorescent tubes, you know, the beam shaping optics was bulky because the sources were bulky, and relied mostly on reflection and refraction. After invention of LEDs in lighting industry, the the systems start to be miniaturized, and this is when micro-optics came into the game. But at the same moment, we realized that besides the reflection and diffraction, we can also use diffraction, because the emission volume of the light sources became quite small, so the spatial coherence was already good enough. And by using this principle, we can shape the light just by a very tiny, very thin layer of the relative nanostructure or microstructure on top of the surface. In our case, for most products, the typical depth is just a few microns, like 2-3 microns, rarely up to 10 microns. It has two principal benefits. One is that you can create from every single point on the surface of the optical element, you can create a whole distribution, so it's not just bending the rays one to one. But because this relief is very shallow, so instead of plastic processing techniques like molding or extrusion, we can use something that is much closer to printing, like potable printing or UV casting, and of course it can have roll-to-roll version, so it's very effective. From product's perspective, what does this mean? You know, with the latest advances in LEDs development, they are becoming smaller and smaller and more powerful. It makes sense to prepare the optics, which is also miniaturized. So in the end, there is something like luminaire in the form of sticker, which is extremely thin, flexible, and can have a very precise, very well-controlled distribution with high efficiency, of course. But, of course, there are challenges. First of all, we are working with wide light sources. So this is causing a lot of problems, you know. If you have a laser light, it's not a problem to shape it perfectly, to achieve very nice images with a simple, relatively shallow, high-frequency synthetic holograms like this one. Once you use this kind of structure, you're working in first order for white light, you know, there will be a dispersion and the object will be extremely blurred. There can be unwanted orders, there can be unwanted scattering effects. So it's not the way for white light. One of the solutions to this problem is to start to work in higher orders. So this laser rating stands for this high order, it's the order rating, where in some circumstances you can tune it to have very high efficiency for white light in just one direction. Which means that the structures now will look differently, they will be much deeper, okay, a little sparser, but it will be very important to maintain the profile shape perfectly. Honestly, this is quite a rare case. On most of our products, you will find something like this, that we are combining, let's say, frenelized, relatively sparse structures with high frequency. It seems like random noise, but it isn't, which is absolutely necessary to, let's say, maintain the good properties of the white beams for illumination, to achieve perfect color stability and smoothness of the beam. And last but not least, there is a problem of distortion during replication, because all of these features must be maintained in the replication process, of course. Okay, so how to produce nanostructured optical components? There are four main parts in the mass production process, and we are trying to focus on all of them and to have the key parts in-house. So first, design and simulation. First of all, we have to answer the question how the nanostructure should look like to shape the light in a proper way. Fortunately, there is usually a lot of degrees of freedom, which means that you can achieve the same optical function from a wide variety of different structures. So it's a good idea to try to search for that one which is the most robust perspective of the mass replication process. Anyway, what seems to be the best approach is to work with experimental data, so we already have a huge library of structures which went through a whole fabrication process, so we have the measured values, and we are using these values to design new optical elements, because this is the only way how to include all the distortions which will appear on the way to the final product. From mastering perspective, we have a lot about it already today. We are using three main tools: electron beam lithography, grayscale UV lithography, direct writing, of course, and R2BP systems to create different types of structures. Tooling, in our case, it's based on, say, optical electroforming, because we are coming from holography, and this is the preferred way there. For purposes of optical elements, we upscaled the bar, so we are now able to produce the tools up to 2 by 1 meter in size. So this is one of the production tools for 1.5 meter long luminaires. And finally, mass production. Of course, roll-to-roll is the most effective process. We are doing both hard embossing and UV casting, but we are also doing standard repeat embossing focusing on different surfaces. And here is also one of the key problems from business perspective, because we already learned that one of the biggest issues when you would like to push the luminaire manufacturers to do some structures is they don't know how to do it because they do not like films. They are working with films, but there are a lot of problems how to handle films because of they are flexible, because of there is no space, there are no features to attach the films, and last but not least, they can be distorted over the time. So this is why, besides these techniques of mass replications, we started to search also for other techniques which can help our partners to apply nanostructures. So the question is, how to apply nanostructure optical lighting systems? And I'm going to present to you two ways which are quite innovative, I think, and they have something to do with plastic processing techniques like injection molding and extrusion. We developed the technology for application of nanostructured films in the injection molding process. I know you can put a metallic insert in the tools, but it's quite difficult to etch the structures to the tool if they have 3, 4, 5 microns, and you must focus on the precise relief shape. So instead of metal inserts, we are using plastic inserts, the film, which will remain in the tool, and which will then be used for a function. So we are using the ready-made nanostructured film in the tool, and then we are injection molding the same material as the base material of the film. Film is melted, but the structure is maintained, and the product is here. So it's a very effective way how to apply nanostructured film on the plastic surface. As you can see, you can curve it by the way during the process. And in the end, there's just a single piece of the final component with the structure on top. So we are able to comb the film without any impact on the surface, the nanostructure, so it's not distorted. And currently, just for example, we have one customer that we are delivering more than 300 kilometers of optical film per year. So this is the product. This is the cylindrical cover, which is fully covered with the nanostructure from inside. The luminaire is called Optical. And the nanostructure is improving the performance of the luminaire because it's a, let's say, single component element. The cover is simultaneous with the optics, so you have high efficiency, well above 90%. But you have simultaneously good light distribution, so you are saving the number of luminaires you need to illuminate properly the space. And when I'm speaking about injection molding, so I must mention also the extrusion, because extrusion is maybe even more popular among the manufacturers of optics for luminaires. So we focused on the process of extrusion, which usually when you are extruding plates looks like this. You are using calendar cylinders to calender the final plate. And of course, what you can think about is to put the tool somewhere, for example, on the cylinder, and to create directly the product with nanostructure on top. Of course, the process is not as simple as this. It's not enough to put just the tool on the cylinder, but there are some tricks, and if you will use them, you can end up with the product with nanostructure without significant distortion. So this is the polystyrene plate, 1.5 mm thick, which was directly extruded with nanostructures on top. The quality of the nanostructure is more or less comparable to that of, let's say, hot standard embossing. So the fiber of the structure is very nice. Okay, so let me just briefly show you some products. So the product portfolio of IQOS Nanotech is quite broad. We have many films, rigid plates, curved components, and also some complex optical systems with multiple components combining refractive, reflection, and diffractive elements in the same system. I will end with a demonstration of one of the product family, which is not the most complex, but it represents very well the idea which was at the beginning, just to get rid of complex optic system and have one flat element to do the job. Of course, it's not always possible to do everything with one element, but in some cases it is, and this is the case where we are applying our linear product, which is flat optics for linear luminescence. So you just take a plate, install it in front of the linear light source. It's not too restrictive to the light source, and you can get different distribution depending on which product you will use. Macroscopically, they look the same. Microscopically, there is arrangement of micro and nano features, and just by rearranging the layout, you can So let me conclude. I hope I convince you that nanostructure optic can give the lighting system completely new optical functions, and by the way also new visual appearance, which is very important in some cases. Can work effectively with polychromatic lighting without any significant color distortion. Can be effectively manufactured in large volumes in roll-to-roll techniques, and can be applied in curved surface directly in industrial processes of injection molding and extrusion, which is a very important aspect if you would like to bring new products to the market. And because of all this, we hope that these structures will play a major role in new concepts of lighting system in the near future. As I mentioned at the beginning, it's going towards the very thin miniature luminaires with high density of light sources and with precisely maintained or precisely controlled light distribution over the space. So thank you very much for your attention, and if there are any questions, I will try to answer.